Today we're going to take a look at slant asymptotes. So this is when your polynomial is top-heavy, but this time it's top-heavy by simply 1 degree. So the difference between the top exponent and the bottom exponent is just a difference of 1. When we covered them before, we did talk about polynomial being top-heavy, and we were talking about a slant behavior. So we're like, oh, it's got a slant asymptote parallel to, and then we talked about, the coefficients, the ratio of the coefficients, and then the difference of the exponents. We said the keyword was that it was behaved parallel to. So just like when we were talking about discontinuity in polynomials, whenever you had P of x and Q of x, we talked about Q of x was where we had points of discontinuity, and those points could be one of two things. They could be an asymptote or they could be a hole. Well, we learned about discontinuity first, and then we went into specifics about maybe what they are. The same is true with our slants today. We talked about how they behave, and now we're going to get more into the specifics. So if we take a look at your first polynomial, we can see, or the rational, you can see that the leading terms here have coefficients of 1 over 1, but they also have exponents of 3 and 2, so there's that difference of 1. So we can say that it behaves parallel to the coefficients, so those invisible numbers here, and then the difference between their exponents. So a line parallel to y equals x. Well, if you notice the image here, y equals x is actually this line in black, and the asymptote is in that blue dashed version. And that's why we were very, very clear about saying it behaves parallel to. But today we're going to look at how to actually come up with that equation. When you have the image, it's easy to tell because you could just do y equals mx plus b. But in order to do it kind of long or by hand, we're going to use long division. I like long division. I'm just kind of old school, so it works for me. But some of you learned about synthetic division when you were in Math 3. Synthetic division is quick, but synthetic division does not account for like greatest common factors or things like that. So I like long division because it makes sense in my brain. I'll show you synthetic division maybe when we're in class together. But I want to start with like an old school example of long division. Let's say, let me see if I can get this to go away. If I had, let's say, 3 divided into 515. Well, old school math would say, how many times does 3 go into 5? Or what do I have to multiply 3 by to get a 5? I multiply by 1. 1 times 3 is 3. You take the difference of the 2. You get a 2. Then you bring down your next value. So you bring down the 1. 3 times what gives me 21? That's 7. So 7 times 3 is 21. They have a difference of 0. You bring down your last digit. That's a 5. 3 times 1 gives me a 5, or gives me something less than 5. So I take the difference and I have a value of 2. That 2 is referred to as our remainder. So this concept of long division we're going to use when dealing with polynomials. So we're going to take x squared minus 2x minus 3, and we're going to divide it into x cubed minus x squared minus 4x plus 4. If we look at our polynomial on the inside, notice that it doesn't have any missing terms. So it had exponent of 3, an exponent of 2, an exponent of 1, and then your constant value. So we weren't like having any holes. So what I do is I say, what do I have to multiply x squared by to get an x cubed? Or x squared times what gives me x cubed? That would be x. Just like we said, what does 3, how many 3's show up in a 5? How many x squared show up in an x cubed? 1x. And if you notice here, we did that 1 and that 3, we multiplied them to get your product here. So we're going to do the same thing. We're going to take x and we're going to multiply it into all 3 terms. And when I do, I get x cubed, negative 2x squared, and a 3x. If we come back to our example, notice what happened after we multiplied. We did subtraction. We're going to do the same thing here. We're going to take this product and we're going to subtract it. So x cubed minus x cubed gives me 0x cubed. What I like to do is actually distribute my negative in, but some people don't. And the thing is, like, a lot of people are going to struggle to see this. Okay. So if you want to distribute your negative in, you could distribute, and then it could go away. So you're doing vertical math. So x cubed minus x cubed gives me 0x cubed. Negative x squared plus 2x squared gives me a positive 1x squared. Negative 4x plus 3x gives me a negative 1x. After my subtraction, I bring down my next term. And I do this all over again. So what do I multiply x squared by to get x squared? I multiply it by 1. When I do, I get a product of x squared minus 2x minus 3, because I take that 1 and I multiply it to each term. And then we subtract. So again, if you don't like having that negative out, you can distribute it in, which simply changes all your signs. Then it's gone. Then you do vertical math. So 1 minus 1 is 0. Negative 1 plus 2x is 1x. And 4 plus 3 is 7. There's nothing you can do that turns an x squared into an x. And so this down here is referred to as the remainder. And what you divided by, or what your quotient is, this is actually your slant asymptote. And if we look at the graph, we had a y-intercept of 1, slope of up 1 over 1, up 1 over 1. So our slant asymptote came out to y equals x plus 1. So you're just being very, very specific. Let's try another one. Again, I'll show you synthetic division in class. Again, I like long division. Synthetic division is fast, but it does not account for GCFs. Long division takes care of that. So sometimes, doing a little bit longer math in the end takes care of all of the little details, while synthetic division may be fast, but it leaves out some crucial details in that mathematics. So I look at my numerator, I look at my denominator, I see, hey, these have a difference of, their exponents have a difference of 1. So 2 in the top, 1 in the bottom. and I set it up, x minus 3 divided into x squared minus x plus 2. I look, these are in order, there's no holes missing, and so we just do that process all over again. What do I multiply x by to get an x squared? I multiply by x, or x times x gives me x squared. X times minus 3 gives me minus 3x. I take the difference, I distribute that negative sign in so it disappears. That way I can add and subtract straight down. X squared minus x squared is nothing. Negative x plus 3x is 2x. Bring down my next term and do it again. X times what gives me 2x? If I multiply it by a 2, I get 2x minus 6. I subtract the whole thing. Distribute your negative in, and you end up with 2x minus 2x is nothing. 2 plus 6 is 8. This 8 is called my remainder. And so my slant asymptote is x plus 2, or y equals x plus 2. If I look at in behavior, that means this graph, this slant behaves like this. So if I look at in behavior, as x approaches negative infinity, my y value, as x approaches negative infinity, my y value approaches negative infinity. And as I move towards the right to positive infinity, f of x approaches positive infinity. So I use that slant to be very specific in where it is, but also tell me about end behavior. Let's do g of x. This is one, again, I like long division because if we look in the denominator, we do have a GCF of an x. Synthetic division, we would have to do a whole bunch of different steps just to take care of that GCF. Long division kind of takes care of it for you. So we look at the leading terms. Their exponents have a difference of 1. So that just means that the long division is going to be a lot easier to do. So I set it up, 2x squared plus 3x. Make sure that as I'm writing this, none of my terms have holes. So there's a cube followed by a square. Notice that there is no x value. Like it goes 3, 2, and then constant. So the x value is missing. So this is one that you would fill in your missing term with a 0. So I would say, there's some cubes, squares, linears. So fill in those missing pieces, followed by a negative 5. We repeat that process. 2 times what gives me 6? That's a 3. And x squared times x gives me x cubed. This gives me a product of 6x cubed plus 9x squared. Look at the difference. I'm going to distribute it in. Notice this becomes a negative and a negative. 6 minus 6 is nothing. 13 minus 9 is a positive 4x squared. And then bring down your next term, which happens to be a 0x. So 2 times 2 gives me the 4. X squared times 1, or nothing, gives me that x squared back. So I have a product of 4x squared. My pen is dying. Plus a 6x. I take the difference. Notice that my product is wrapped up in parentheses so that I don't lose that negative. Distribute it in, so this becomes a negative, 6 becomes a negative. When I distribute it in, again, it just lets me think of things vertically. So 4 minus 4 is nothing. 0 minus 6 is negative 6x. I draw up my next term. Nothing that I do from an x squared will ever give me an x. So this would be referred to as the remainder. So if I asked you what the slant asymptote is, the slant asymptote is y is equal to 3x plus 2. Oh, my pen is dead. There we go. 3x plus 2. It behaves like this because it has a positive slope. So kind of old school right here. So if I asked you the limit as x approaches negative infinity, you could tell me, oh, well, that side points down. The limit as x approaches positive infinity, that graph points up towards positive infinity. So that slant kind of gives us, a twofold. And then you can tell all other key features from this. You can tell horizontal asymptotes, you can tell holes, you can tell vertical asymptotes, kind of like all the things that we've been doing. So we're just building on what you already know. There are a couple questions to practice with the Delta Math. I think there's only 6 or 7. I try to keep it very short. Long division, I know it seems like really intense, but it takes care of all the nitty-gritty details for you that synthetic division won't always do. And again, as when I come back and we see each other again, I'll make sure to go over synthetic division. Some of you might like it, and we'll just talk about the pros and cons of both methods. You find the one that works for you and get really good at it.